Hey YouTube, Electric Adventures here with the next episode of Let's Make a Retro Game. Sorry there's been a little break in the series, although if you started watching them now you won't notice. Some health issues which I now have sorted, and finally got the time to do the support material for this episode. Each of the episodes is getting slightly more complicated as we're getting into more advanced topics. And also an aside, the next episode, rather than make progress on our actual game, I realised, based on some of the questions you guys have been asking, that I need to do a little bit of a side topic just to build up some more technical knowledge on the systems we're programming for. So, it's a little snippet of what's coming next. So, what is the series about? Let's Make a Retro Game is a series about writing in assembly code for multiple different systems, and basically we've selected a particular game based on a game for the Intellivision called Astro Smash. So that's what we're basing a game on, because it's a fairly simple game. It just involves a ship that moves back and forth down the bottom, and then things float down the screen, and you can shoot them and you lose points when it hits the bottom. And it's a fun game. It introduces some simple concepts and allows us to work through the various topics that you need to cover when you're making your own games. And hopefully this series of videos will inspire other people to write their own games for old systems. Now, we are going to cover a lot of systems, but I am focusing in this early part on Z80 programming. So the systems we're primarily covering are MSX, Coleco and the original Spectre Video as the primary systems. Once we get the game working on those three systems, we're going to port it to the Spectrum and the Amstrad, the other two main Z80 systems. We could also do another couple of systems. There's the SG-1000 or SC-3000 from Sega, very similar to the Coleco and MSX systems, and even the Memotech as well. So I'll see how I go with the side videos on doing those. But anyway, on with this episode, because it has been a little while since the last one, so I'm sure everybody is anxious to find out what we're going to be doing. So the main idea behind this particular episode is, at the moment, where we left our game, we had a ship down the bottom, we were shooting, we had one type of enemy, which is an asteroid, coming down the screen and just coming down vertically, and we could shoot it, it could hit the bottom, it decreased our score, and if we shot it, we got score added on. So a basic game, just and you could die and we could lose lives. So we have covered some basic elements, but now we need to make the game a bit more fun. And in this episode, we're going to be adding the structure to allow us to add more enemies to the game later. So we're actually not going to add any new enemies this episode, but we're going to put the structure in place to do that. And it is, a bit more of a complicated topic, but hopefully I'll walk you guys through it, so hopefully you can understand it. But obviously comments down below if you need anything clarified, and I'm happy to answer them. Okay, so enemy management. So at the moment, cross notes, we're only using 1 byte of RAM to indicate our enemies, and it basically has a 0 in it if that enemy object is not in use, and a 1 if it is. Our other information for enemy is stored in the video RAM on the sprite data, where its X and Y coordinates and what pattern it's using. But to make a game where you've got different enemies and you can use the same lot of code, so almost like a generic enemy routine, you need to know a bit more about the enemy. And there's 2 stages. There's the enemy before it comes on the screen, so that's your basic information of what shapes does it use. Does it use one shape, or does it animate through a couple of different shapes, so you get a bit of an animation. We could put some standard things as how fast it comes down the screen. Does it move left and right as well? So we could add some velocity variables as well. So I have prepared a little table. So this is our first thing. So in ROM, oops, I need to move that over a little bit. Sorry guys. Okay, so in ROM, we need to store a bit of information. So let's plan it out. So we need the starting shape. So that's the shape so it's our sprite pattern that we're going to use for the shape when it first appears. And then and the way to do this is you put your patterns in order in a group, and then all we have to do is say what the ending shape is. So then we can write some code that will make it, in an animated sequence, display the first thing, the next thing, the next thing, until it reaches the ending shape, in which it goes back to the start again. So, and dx, which I use d for, it's a calculus standard thing for saying change, so the change in x. So this is saying our velocity in x, so our starting velocity in x, and our velocity of y. What score do we get when we shoot this enemy? How wide is it? Helps out with our collision detection. And just for later on, I've rounded it out to 8 bytes because it makes some of our maths when we're looking up an entry a little easier, and it's always good to save a little bit of space. Now we're talking about, this is space in ROM, and if we run out of space later, we need to get some more ROM back, then maybe adding a little bit more code to calculate where to get something out of ROM by reducing the size of this table might be something we can get some memory back on. But for the moment, I'm going to make it easy to program, and it also allows us to come back and add some stuff later, just in case we need it. So this ROM is, this information is wrong is something that doesn't change. So when you ship your game, this is static, so it doesn't change at all, and it's information used to put your object on the screen and then have standard things that you want to use for that particular object as it moves around the screen. So we'll have a table of data at the end of our in our data section of our listing that'll have this ROM table. Okay, now I'll do this by this. I'm going to paste a little bit of code in here. So now you notice I said that we've made it 8 bytes. This makes it very simple for us to find the address of an enemy. So I'm going to pop the cursor here. So here's a little bit of ZOD code. Sorry, straight into it this episode. So we're assuming that the register A has our enemy type, and that's in a table, and the table entries are 8 bytes long. So we set our HL, which is our address, Z80 register that we use for dealing with addresses, and we set it to the base address of our ROM table. Now there will be a little bit more complex code in the actual thing. This is simplifying to explaining to you. Then we take A and we multiply it by 8. Now, obviously, in assembly code, it is hard to multiply numbers, but it's great when they are factors of 2. So how do you get 8? 8 is 2 times 2 times 2. And the easiest way to multiply by something by 2 is to shift the bytes to the left. So that moves byte. Bit 8 is bit 7 is lost, bit 6 is moved into 7, 5 is moved into 6, all the way down. 0 is moved into 1, and a 0 is moved into byte 0. And what that will do, so if your number was 1, it would double it to 2. If it was 2, it will double it to 4. So we do that 3 times, so 2 times 2 times 2 equals 8. So we'll have multiply that value by 8. And then we add it, and the easy way to do that is we put the A value in C, we zero out B, and we use the add statement to add it to there. And I've just noticed the mistake. Sorry. We don't want to add with carry unless we've cleared it. So that'll take HL and add on the value in BC. So whatever an enemy type times 8 will be added onto this address. So we'll be at the particular spot in our table. So I'm not going to say as simple as that, but it is as simple as that once you understand the basic instructions. So next, we need another table. So whilst our game is progressing, the various parts of the enemy will change. We have our original, remember I mentioned before, our in RAM at the moment, we just have 1 byte that says whether our enemy is in use or not. We're going to reuse that byte. If it's 0, the object is nothing, so we'll still use the same value for 0. But any value larger than that is actually our enemy type. So I've got another table here I've already pasted in here compared to earlier. So our first byte is still going to be our enemy type. And I've defined a couple of ones just to give you an idea. So 0 is nothing, 1 is our existing large meteor, 2 is a small meteor, 3 is a smart bomb, and 4 is an explosion. But, ooh, an explosion, that's not really an enemy type. But what we can do is, if you have a large meteor and you shoot it, we can change the enemy type to be an explosion and then have specific behaviour for an explosion, including not being skipping collision detection, because you don't want to shoot an explosion that's already happening. So you could have, we've got 255 different types we could have here, so there's a lot of scope to have a lot of different enemy types. And then we have here repeats of our dx and dy, because the dx and dy that are in the ROM table are the starting things. But what if you want a shape to be able to move in response to the player or its environment? You may want to actually change its dx or dy. We don't need to use bytes to store the x and y, because we have our sprite table for that. So when we originally create an enemy, we'll copy the starting dx and dy into these RAM locations, and then from then on we'll just use the ones in RAM. Okay, so that's that bit dealt with. Now we're going to get in some code. Now I have added, to make this easy, I've highlighted in the document the parts of the code that are going to change. But to make sure I don't make a mistake, I'm going to paste in the whole routines, just to make it a little easier for you guys. So here is, I'm in the start folder. So in the samples I give you, both for MSX and Coleco, you'll have a start and an end folder. So start is what you want to start with if you want to follow along with this, and end is what your end result should end up with. And hopefully by the time I finish doing this, my start should equal the files in the end. So this is our game. Probably should update the copyright dates there, but that's okay. So the first thing we want to do is put our enemy data table in. So, sorry, I need to get my code pasted. So I'll grab that. Okay, now where do we want to put this? We need to put this down with our other pieces of data that we have. So we go down the bottom. So this is right at the bottom of our file. We have our RAM here. At our RAM start, we're including library here and all of our patterns here. Then we have our main layout and title screen that we've added previously. And there we go. So this is a good place to put our data. So let's plop that there. So I'll like to put in some documentation, so when you come back later you remember what in the world I was talking about. So it's the enemy source data table. We have start shape, end shape, dx, dy, score, width, and 2 spares. And we need to make sure we fill that out as is. So as you see, 1, 2, 3, 4, 5, 6, 7, 8 bytes per things, and there's 4 entries in there. As we're just calculating based on an index, we don't need an ending tag or anything like that. So that step's fairly easy. Next. Right, now I'm going to add a handy function. So let's go up near where we will need to be shortly. Okay, here's our main game loop near the top of the file. And then we have our move enemies. So how about we pop our function just before move enemies? That's probably a good spot. At the end of the day, it doesn't really matter where you put these bits and pieces. Just getting the right thing. Make sure I get it all. Okay, so we're going to put that here. And it is a function called calc enemy. So what does it do? Well, we say what it does here. Calculate base enemy data location in ROM. A equals enemy type, assumed to be 1 or greater. In modern languages you would check parameters inside functions, but that uses up time and we don't want to waste too much time in assembly code. So we assume the person calling this sends us the right data. So yes, this is where crashes can come in later. But once again, 8-bit systems, we need to save on time. Now, it's going to return and use IY. And once again, I'm using the IX and IY. They're not the fastest. You can do things in faster ways using other registers. But these make it much easier to read which I think is a lot more important. Unless you're having actual performance problems and then you can readdress it, sometimes it's better to just use the more wordy and verbal instructions so they're easier to read and use. So OI will be our address in ROM of the 8 bytes that correspond to the enemy type that we put in. Now once again, we need to make sure we can call this from anything and not hurt anything, so let's try and not destroy any registers. So I'm going to use A, HL and D in this, so I push AF, HL and D onto the stack, so they're saved. We set HL to our base enemy types thing. We decrement A by 1, because if A is 1, we actually want the first address in the table. If we left it at 1, we'd end up with the second 8 bytes. Now, if you multiply 0, even if it's 0, if you multiply 8, it's still going to be 0, so that's going to be fine. And I actually notice we've got a mistake there. Come back to I'll have to fix the template before I save it. Okay, so it's the code I showed you before, except I'm using DE instead of BC. So I put A and E, 0D, or A. We don't need to do that if we use add. HL add on DE. So now our address is right. So we want to put it in IY. Quickest way to do that is to push the HL onto the stack and pop it straight off into IY, and then making sure we do them in the reverse order if we push them on. Pop DE, pop HL, pop AF. So this whole bit of code, all we have done is change to IY. A is back as it was, as passed in, because the calling code might want to use it for something else. So there we go, that's that function finished. Yep. All good. It's good to compile as you go. So, next. Oops, I clicked on the wrong thing. Now, a little adjustment. We need to allow a little bit more RAM. So if we go down and have a look at the moment for enemy data, so we're saying we can have up to 20 enemy objects on the screen, and we're allocating 1 byte of RAM for each one. Well, now we're using 3 bytes of RAM, so we need to multiply that by 3 and allow 60. And of course we need to initialize that RAM. So where's our init RAM function? Now I'm just probably doing this slow. There it is. So here's our init RAM function. So this is where we, because you can't assume that any spot in RAM is going to have a 0 in it or any value. It could be completely random what's in there. So you need to make sure that you initialize things properly. So we're using a special trick with the LDIR command to do this for us without writing an actual loop. So currently it's doing a 19 plus 1 value, so 20, so we need to make it to 59 plus 1 values. Very simple changes. Now, let's go find our spawn enemies function. Right, the best way to do that with Sublime Text is to go to definition. So the things I'm going to change in this, there are quite a few changes in it. So I'm going to paste in the whole routine and then we'll go through it again. So this is the routine that creates our enemies. So it went to 419 before, so we've added approximately 10 lines of code to this. So let's go through it from the start. So this starting section hasn't changed at all. This is just getting our current level of difficulty, and then that defines our range for calling a random number and whether or not an enemy is going to appear. As I've previously commented, we can do some tweaking and make that a little better. Okay, so when we've decided that we want to display an enemy on the screen, we want to loop through our enemy data, and remember we've only got 20 of them, so we don't need to change any of this, and we need to find one that's not in use. So still, anyone that's 0 isn't an enemy at the moment, so we can reuse that one. So we loop through until we find one of those. I'll show you the end of the loop in a minute. So an enemy is available, and we're saving HL, calculate a sprite memory position. All this is now, yeah, this is new code here, because we now need 3 bytes to determine which is our memory position. We haven't kept a counter to the we've only got the base address as HL. So what we do is we go and add sorry, this is calculating our base sprite position, which is actually exactly the same code as before. I've gotten ahead of myself there a little bit, so that's actually our sprite memory position. That's fine. Okay, and we set our X to a random value. That's the area that needs improvement, because remember, sometimes the asteroids appear just a little bit off the right, so we need to fix that later. We set our pattern, we set our colour. At the moment, we're still just going to make enemy type 1s appear on the screen, but we'll hardwire it to 1. We'll call our calc enemy to get our base ROM address, and then we will put that obviously in our first memory address increment, and then here we go, here's our IY, so we get the DX and we store that in where HL is pointing to, increment again, and store that one in the next memory address. So we've stored 1, whatever the DX is out of the ROM table, and whatever the DY is out of the ROM table, and put in that memory, and we're finished, so we can return. We don't have to worry about incrementing HL or anything like that. Now, while we're finding the other little change, so if the value's not 0, we go to the next memory location, and now we need to move 3 addresses, so we have repeated inc HL 3 times to skip our 3 memory addresses. And this decrement jump if not 0 is still the same, and it's a small range, so the statement will work. So not a lot of actual changes in there, just a little bit here to go and grab some values out of our ROM table and to hardwire an enemy value to 1, which we were doing before anyway. We were putting a 1 in there just to say an object was on screen. But in this particular case, it means we want a large asteroid. Later on, we'll actually utilise some more logic to select at random based on a random number which object is going to appear. Next, now move enemies. Now there are quite a few changes in this one. I believe this is move enemies here. So move enemies here. So once again, I'm going to paste it in and then the whole thing in, and then we will go through the changes that we've done, and that way it'll act as a bit of a refresher. Now there are quite a few changes in this routine, so you'll have to bear with me. So currently starts at 205, and as you can see, it's fairly long and goes to 328. Sorry, my silly mouse has clicked off. Right. Oh, sorry, I didn't say where it got to. So, yeah, we're adding about 20 lines. Not too many, but, and we are changing some things. So I'll just get my notes up. Okay, so we're looping around our enemy data. Once again, 20 times, maximum 20 entities. We do our same check to see whether it's 0 or not. If it's 0, we go around and do another loop. So that jumps down to ME2. The change here is we've got 3 increments of HL. We decrement B jump. Now we have to use jump because it's a larger range. This animation timing is the same, we haven't changed it. So let's go back up to the start of our loop again. Now, it's calculating our sprite memory position doesn't change. Get our enemy data, so we need to get out of HL what type of enemy it is, because it's not necessarily going to be 1 in the future, it could be something else. So using the value in A, we call calc enemy, and that will get us wipe to our ROM data for the enemy so we can use it. We have our animation logic here, so if it is time to animate, so this animate flag controls the delay. So we're calling this move enemy routine every interrupt, and this animate things allows us to slow things down so we don't actually animate the object all the time, and that way you'll be able to see it. Right, so at the moment, so we get our current pattern. So remember, IX is pointing to our sprite table, so +2 is our current sprite definition. We add 4 to it, and does that equal to, this is our ending pattern in ROM. If it doesn't, well, if it does, we set our shape back to, out of our ROM thing, our starting shape. So in the ROM table, you should set the values to the actual starting shape, and then 4 after, because we're dealing with 16 by 16 sprites, they've got 4 shape entries in the shape table. 4 bytes afterwards. That way we don't have, once again, don't have to do any mess at this moment in time. It's just a straight comparison, and this is how you speed things up, just by changing your data a little bit. And then we store whatever the value of is A back in our RAM table, which is holding our sprite data. So we've gone and changed the shape of the sprite when our animation time is up. Very simple bit of code. Now we get our current Y position out of our sprite table. Okay, we need to go and get our change in Y from our local data table. Now we are using HL for that, so we don't have an offset thing we can use there. So in this particular case, we've got to increment it twice, get the value, and then decrement it back, so HL is back. You can actually, you still have to do the 2 increments. It's borderline, because in incrementing and decrementing quite fast, so is a pop and a push. We'd have to address the timing, so there's another thing where timing could go either way, but you could actually push ink twice, do that, and then pop, and you'll be back to the same situation. So homework, go and figure out which one of those 2 methods is the fastest, and let's talk about it. Right, so we add our change to E, or E we add to the change, it doesn't really matter which way we do it, and we see whether we've reached the bottom of the screen, and using carry rather than a precise value allows you to have faster vertical movements, like you could be moving at 2 or 3, and as soon as you've gone past 150 at all, this will trigger. So if there's carry, then the number we're comparing is smaller, so we haven't, is larger, so we jump to ME3 and we keep on going, but otherwise the enemy's reached the bottom of the screen. So the first thing we do is we check to see whether we've hit the player sprite, and the easy way to do that is to grab the player sprite's X, we subtract the value in our data table, which is the width. So this is in our ROM table, not in our RAM table. We want the width of the enemy. We compare those, and using, so if no carry we've missed, then X plus its width is larger than the player's X, so this is doing, so we're basically comparing the bounds. You have to go back to a previous episode to show the diagram, and it's a way of comparing whether 2 objects have hit within their widths and their range on the X-axis, and you do exactly the same for comparing on the Y-axis, but we already know the sprite is at the level of the player, so all we have to do is check it against the player's X coordinate. And you can see how we're easily using our ROM table value for the width there, and comparing it against our actual X value in our sprite table. So all very easy to read in very few statements, just that these ones that use the offset ones do actually take more opcode, so they perform slower. So if we get to this stage here, we have actually hit the player, and this is when we decrease our lives and see whether there's a game over and things like that. That's all. That code hasn't changed at all. We don't do anything when the player dies as far as animation and everything like that, and we continue on with our loop. Right, if we didn't hit the player, we reach here, we've reached the bottom line. That means we need to decrease our score. That hasn't changed from before, so we lose 10 points if any object reaches the bottom. There will be a special case for the smart bomb later. It'll actually cause a small explosion based on the original game, but we'll deal with that later. Next, the object needs to disappear. So regardless of which one of those, we need to get rid of the object. So we clear it out in our RAM table, so we can reuse that object, and we clear the actual sprite as well, and then jump to the end of our loop. Now we've actually finished our movement of our Y, so we store that value back in the sprite. So enemy object is moved, now do collision detection. What's the other thing we have to do collision detection against? It's our player's bullet. So that's stored in the third sprite, because we're using 2 sprites for our main ship to make it more colourful. Well, first we do is we check to see if it's on screen. If it's on screen, we don't need to waste time doing the next part of the calculation. We save some of our registers so we don't lose them. Once again, we're going to use our width, and we're going to use our general collision to test function that we've used before. So nothing much has changed here, except the width value, which was hardwired here for a particular asteroid, is now being taken out of the ROM table for that object. So this collision detection will now be able to handle any of the types. Now, I will say, at the moment we're only storing width. Later on, one of the things I might want to add is a height, because you can actually, we're dealing with square objects at the moment, but what if we're not? What if we have an object that's taller than it is wide? That's when you might want to store the height as well. Once again, an extension for later. So we fill this out, and the only change in this section of code, these 3 statements replaced one that hardwired the width and the height of the sprite. Now, because it's the same, we just copy them into both values. Call our collision detect, get our registers back that we needed. Our carry flag will still be set if we've got a hit, otherwise we'll jump past the end of our loop. So we have a hit for the moment, just makes both objects disappear and add our points on. But here's another little change. Where do we get the points from? From our ROM table rather than the hardwired value that was there before. We still need to do an explosion and stuff like that. So what we would do would then change this object type. So instead of this deactivating the enemy, we actually change the type into an explosion. And we would make the explosion when it ends its animation run to disappear. That's how we can get. That's how we'll get that going later. So, won't cover the next episode. We'll do, because I'm going to do that side episode. We'll do it the episode after. Right, and here's the end of our loop. So here we need to make sure we increment HL 3 times, which I've sort of already covered. Decrement B, jump around. So we've actually gotten to the end of our code changes. Let's check to make sure I haven't missed anything. Right, that's pretty good. So we should save, and let's see if I've managed to do this correctly. Well, it builds. Now let's open our emulator. Sorry, I should have had this open earlier. Check our emulation. Yep, we're on MSX. Okay, we select our Megabass ROM from our correct folder. And hopefully we've got this right. So, that title screen comes up. That's always a good start. Right. So, we've got large meteors coming down. We can shoot them. The meteor is shimming a little bit, so I think our animation's sort of working. I need to work on better shapes for this. Any creative artists out there that want to do some different enemy types with this, feel free to do them and send them in. This is a project to be shared by everybody. Whoops, got killed. So everything is working as expected. So a little bit anticlimactic, because the game, the game doesn't actually do any more than it did at the end of the last episode. But now we are ready to move forward, and we've covered some quite advanced concepts. So once again, I do apologise for the gap between these episodes, but they do take a little while to prepare. Now, support material for this episode, so a full article of what I've covered in words, will be on my website. I'll put a link down below. Also, the source code. Currently, I'm giving you the source code for MSX and Coleco. I have a little bug in the Spectre video version at this stage, so hopefully by next episode I'll be able to give you that one as well. And I may actually start working on some of the other very similar compatible machines like the Memotech and the Sega SG-1000 3000, and get them up to speed in the next couple of episodes, and try and keep them all up to date as we work our way through. Right, so any questions, please feel free to ask them down in the comments, and I'll try and answer them to the best of my ability. This is a tutorial for everybody out there who wants to learn and follow along, and all input is welcome. So I hope everybody has enjoyed this next episode in Let's Make a Retro Game. I really do enjoy making these, and I'm really happy to be back making them again. I'm Electric Adventures. Thanks to all my subscribers. Thanks for watching, and I'll catch you next time.